All right, so this is going to be part 2 of learning policies from our models in RL. So last presentation we did guided policy search, where we had continuous state and action spaces. The dynamics were deterministic, and our teacher adapted to our parameterized policy that we are learning. So in this presentation, we'll be doing imitating optimal control, so imitating our model using DAgger. I'm going to go a bit more into DAgger. That's like an optional digression, and some more general questions about why we'd want to create a policy again. And then we will wrap up by summarizing model-based RL and by comparing it with model-free algorithms. Let's jump in. So last time, this may look familiar. Again, continuous actions, state and action spaces, and it's deterministic. And because we make the constraint satisfied ultimately by adapting lambda, our teacher and our policy adapt to each other so that ultimately they end up being exactly the same. Cool. So let's look at imitating optimal control using DAgger. So the algorithm is basically you run your policy, collecting some states, and then for each state, you label what the correct action should have been in that state. You might not have taken it, but label what the correct action should have been using your model. So, for example, it might be Monte Carlo tree search. And then we add this state action pair to our training set. So that's like your input, your output, your XY, just for regular machine learning, and then you train a policy on that. So it's just supervised learning on these state action pairs. So that's just DAgger, right? An example of this, they use this with an Atari game. So they use Monte Carlo tree search to figure out what the correct actions were in order to label the action so they could do DAgger. All right, so here's where you pause the video and think. So to use DAgger, you should collect on-policy trajectories, then label what it should have done at each state, so it learns to recover from its mistakes. So this is all good, but if you're not working with your Atari games, you're working with a car, you don't want the car to actually drive off a cliff. So how might we be able to avoid such catastrophic costs with real robots or cars, but still train effectively so that we can recover from mistakes or suboptimal moves? I'll pause the video. All right. So it turns out that a compromise works. If you collect mostly on policy data, then you can make some mistakes. But you can allow your model to override actions that would carry a really large expected cost. So you allow it to make suboptimal actions, and it will learn to recover from those mistakes hopefully before it makes any catastrophically large mistakes, so that when it's eventually trained, you won't have to worry about it making catastrophic mistakes because it will have learned to correct before it gets there. The car will learn to correct as it goes to the edge of the lane rather than, not knowing how to correct until it's right about to go over the cliff. Cool. So I'm not going to go into this. This is some more of my notes. I'm just showing it here briefly in case you want to read it. All right. Now, we've seen this trick before. We can use different inputs where our model-based planner gets kind of higher quality inputs like the actual state, some low-dimensional, really precise inputs, whereas the policy that's getting trained uses some observations which will be lower quality but actually available when you're driving the car or operating the robot. We can do this trick as well. Sometimes it'll work, sometimes it won't, but we can try it. So I want to discuss DAgger a bit more. So feel free to skip this, but if you're interested, don't skip it. All right. So with DAgger here, we have our model say what the correct action is, and then we're just trying to copy that action, right? So our model is not an adaptive expert. It just says this is the absolute best move if you were to make absolute best moves hereafter in the future as well. So why can DAgger often work, whereas in guided policy search this wouldn't work? Pause it. So my answer is because DAgger collects on-policy data, including deviations from optimal actions, it learns the correct action after it made a mistake as well. So it learns how to correct its mistakes. So that's why the expert doesn't need to adapt, because the expert tells it, even after you've made all these mistakes you make, here's the best move to take. So when can it work without an adaptive expert? So when the policy is capable of matching the expert's behavior closely enough. And this would be, because it has sufficient information and it's basically a sufficient representational power. If the model has access to information that the policy never sees at that point, right, because it can't see into the future like the model can, well then it doesn't matter how flexible it is, your policy might never learn to perform certain actions effectively, right? Cool. So when, for example, might DAgger not work? Pause it. Okay, we just went over this. Yeah, so we could use an adaptive expert in some cases to adapt to what the policy can actually learn, but this might be more difficult when you have probabilistic dynamics or probabilistic policies. Yeah, and I want you just to think, how does DAgger, like using DAgger on like the correct actions from a model, compared to using guided policy search, and what allows each of them to work? Okay, so just pause it and think through that. So I would say guided policy search, you imitate your teacher perfectly because your teacher adapts to what you're capable of doing, right? And so when you can do this, this works awesome. But this is only 100% possible, as I understand it, when you have continuous state and action spaces, it's deterministic, and when your policy is only being trained on the paths that it will encounter, right? If you want it to generalize to starting at a new location, well, this won't work perfectly. It might work well enough, but it won't work perfectly. But as long as you can imitate the teacher perfectly, then you don't need to worry that you're going to make some mistakes and then your policy won't perform well, so you'll make more and more mistakes and you'll get more and more off track. You don't need to worry about that problem because you imitate perfectly. In DAgger, it's a different approach. So we imitate like our perfect tree. We try to imitate our perfect controller, but we do that imperfectly, which is why we require on-policy data so that we can learn how to correct when we make moves that are not optimal. So I see this working better, working well for probabilistic policies. I see this actually as being kind of a more general approach than guided policy search. So guided policy search might have a narrower scope of application where it actually works really well. All right, so that's the optimal part over. All right, why imitate optimal control? Well, so it usually works well to combine supervised learning with optimal control, because optimal control works well, supervised learning work well. Optimal control is very sample efficient, so you benefit from that. You can also use some tricks like the input remapping trick. Right. You can use your model with avoiding the pitfalls of backpropagating into your policy directly. Yeah, that's about it. Cool. So now we're going to look at, big picture model-based RL and how it compares to model-free and when to use which. All right. So we can, if we just use the model, then we can do some planning with our current model, and then based on that new data that we collect, we do some new planning, or we make our model better because we achieve new states with our improved model, and so we need to actually better model those states. And so you just iteratively use your model for planning to collect more data, then train a better model and repeat. Generally, it works best to replan at every step, so that's the agile approach. Model predictive control is what MPC stands for, and so that allows you to correct for small errors due to your model. At the next time step, you see, oh, actually I ended up here, and you can correct early on. You can also, after you've learned a model, you can learn policies from that. So you can backpropagate into your policy, which doesn't work very well if you have a lot of time steps, exploding and vanishing gradients issue. You can imitate an optimal controller with a constrained optimization framework, so guided policy search, or we can imitate via DAgger, a DAgger type approach, which we just looked at. And yet another approach is to generate synthetic data using our model, so that we don't actually have to run our real robot. We use our model, generate synthetic data, and we can train a model-free approach on that. Yeah, so these are some model-based RL approaches. Let's compare model-based to model-free. Let's make that larger. Cool. So model-based tend to be very, very efficient, and so that's them here. And shallow RL models can be actually way more efficient. You use Bayesian type stuff. You can control for overfitting better. But I think these they aren't as general. You can't kind of throw them at any problem as much. But for specific problems, they work extremely well. So then Q-learning, off-policy model-free approaches require about 10 times more data, but they're still fairly efficient. And then you can do these, somewhat off-policy things like TRPO and PPO. They require about 10 times more data again. And then you can do fully online methods like A3C, but they require much more data yet again. And then there's things like, genetic algorithms. So gradient-free methods like that require even more samples. Yeah. Now, so you get more sample efficient as you go down here, model-based being very sample efficient. Now, wall clock time is the reverse. So genetic algorithms, you have a bunch of things running in parallel. So if you have a massive parallel cluster, you can parallelize very, very well with genetic algorithms. So you can actually, in terms of wall clock time, you can have things converge very quickly with unlimited computational and simulation resources. And yeah, so apparently it's reversed. So this leads to when to use each RL algorithm. Let's make that larger. So generally for robotics, which is where we've actually seen a lot of this model-based stuff, that's where we want to use models. We could maybe, if we're not too concerned about efficiency, we could use Q-learning. I have seen some other approaches used for robotics. But yeah, we tend towards the sample-efficient approaches. When we have a simulator, or we're playing an online game, well then some of these model-free approaches are probably better. And depending on the simulation cost, we might want to go with Q-learning, or we might want to go with PPO, that kind of approach. Yeah, so I found this quite helpful. And there's also, you can combine approaches, right? You can train a model and use that model to train an initial policy, and then use that policy as your starting policy for TRPO. Sorry, I don't know why I was pointing at this, but use your model with DAgger or whatnot, train an initial policy, and then do PPO to tweak it and really get that performance, right? Yeah, another thing that I hadn't mentioned, which I'll mention again, is once you have a model, if you can change your objective, right, kind of change the reward function, or which is basically changing the task, you can execute different tasks with the same model as long as the model is valid. Right, that you could have the distribution mismatch problem, but actually you can perform a lot of different tasks in robotics using just a model that was trained on random motions. So, yeah. So this completes Sergey Levin's 3 lectures on model-based RL. There's one more lecture by a guest lecture. So as part of Sergey Levin's course, but there's a guest lecturer, so I'll be going over that in the next video. And then we'll also be looking at some papers and how they applied model-based RL and to real and simulated robots mostly. All right, thanks for watching.